I'd like to have the honor of bringing up the first team presentation. It will be Team University of Saskatchewan. Ty McGee will be representing the team, and their presentations on exploring the Yukon-Tanana terrain through time, space, and scale via the integration of open source data.
Forward, back, and that's the laser.
Awesome.
You got two of them, so you want an extra water?
Oh,
We'll swap.
Thank you.
Over.
All right. Thanks everyone for coming today. So, like they said, represent Team University of Saskatchewan. We didn't have a clever name like everyone else, unfortunately. Again, Ty McGee, co-authors Colton Vesey, Matthew Nadeau, and Todd LeBlanc. And we're going to focus on talking about integrating open source data, specifically in the Yukon-Tanana terrain. So here we have the map from the Frank Arnott competition with available data sets. And like we said, we're going into the Yukon area, so let's zoom in. So focusing on our project area, here we have a bedrock geology map. And the first thing that we noted when we looked at this is it's quite complex, geodynamically, structurally. The other thing to note is that it hosts various types of mineralization, which is quite unique. Not just one type, but porphyries, VMSs, SEDXs, and MBTs. As a preface for our project, we focused on porphyry exploration. The other thing to note about this area is it's characterized to be quite a mature landscape with poor outcrop exposure and locally thick vegetation. And with those kind of reasons, there needs to be different types of exploration in this area. So this goes into our concept or our outline. So we want to generate visual interpretations using only open source data, either provided by the Frank Arnott project or some other public domain. Using this data, we want to correlate these multiple disciplines, including geology, geochemistry, and geophysics, with known melogenic events through space and time. And we'll do this in 4 ways. We want to create a new visualization tool to view the reconstruction of the Cordillera using G-Plate software, create a new simplified lithology model of our project area with known melogenic events, and then lastly, process and generate regional magnetic and radiometric data and stream geochemistry maps. So overall, we want to integrate all these techniques to possibly identify preferred metal districts in our area or find regional targets. So here we have a bedrock geology map of our area. Outlining in the black is our Frank Arnott competition area. If we're going to find regional targets, we need a regional understanding. So not only did we extract from the Yukon Geological Survey, but also the geological surveys of Alaska and British Columbia. So each of these colors represents a specific unique ID, could represent over thousands. First thing that we see here, it's quite confusing. A lot of disparities between borders and provinces. So is there a way to look at this in a more simplified term? The other thing to note is when we were looking at the databases, there were a lot of insufficient absolute ages, meaning that there were a lot of relative ages. So this will come into play with one of our other analyses. So the first thing we need to do is we need to restructure this. So by using Microsoft Access and structured query languages, we were able to group the complex geology into 7 main lithology types with subclassifications if we need to specify any further. So on this map, we have more particular interest in the magmatic and the volcanic, so red being plutonic and purple being volcanics. But the first thing that we see here, we see obvious magmatic belts, and we see these linear trends all across borders. So this is extremely useful for us. So one of the things we also did was we added minimum and maximum ages to all the lithology types. This was able to help us produce a 4D model using G-Plate software. So here we have, in context, Greenland and North America. Highlighted in the white square is our project area. And then if you guys need reference, time frame. But as we start this, we're going to start seeing the plate tectonics move. And we're going to see dots appearing from red, blue, gray, and green. And these can represent plutonic, volcanic, coolant, and metamorphic ages. But the reason why we want to look at this is it's to understand the geodynamic setting of our area. And if we understand this, we're going to ultimately understand what type of mineralization we could possibly see in this area. So here we're starting to see some of these terrains start to accrete, thus producing the Cordillera that we see. seeing this, we're going to see a lot more red and green dots appear, which would be the plutonic and volcanic ages respectively. As we're seeing this, we're going to start hypothesizing, okay, well then maybe there are porphyries in this area, in a regional setting, of course, but we're starting to see this linear trend, not just in our area, but across North America. And then soon it will be up into present day. So zooming in into our project area, again, bolded outline is our competition area. Using time sliders on ArcGIS, we generated from 450 million years to present day. The rock classification scheme represents the colors that we see here, but we're starting to see more ages, and we can start distinctly seeing what type of magmatic belts that we want to look at, and possibly find linkages to possible porphyry exploration. So we're going to see a lot more magmatic belts arise around this time frame, and then continue on to present day. This also kind of helps us bolster when we look at the G-plate software, seeing these accreted terrains, that we would see these types of magmatic systems. Now that we have a simplified lithology database, we want to group this with known metal districts or hypothesized metal districts. So in the database, there was also known deposit models and, deposit and prospects and data points. So highlighted in the red circles, if you can see, are all the known porphyry deposits and prospects. So we can't really generate any trends with this. Maybe we could see, but we need to base this with lithologies, possibly with our simplified lithology model. So using Allen et al. 2010, they comprise all the radiometric data from various deposits. And they comprised 5 main metallogenic ages. So we're able to query this and only show lithology shapefiles that associate with those metallogenic ages. So going into the 5, we have the Devonian to the Permian, the late Triassic to early Jurassic, the Middle Cretaceous, the late Cretaceous, as well as the early Tertiary. This is extremely powerful because now it's not just saying, oh, we have some porphyry data sets, so that's probably the trend. We can now associate it with lithologies and maybe extend those trends further. And the other thing to note is if we have stuff from the early Tertiary, we might not necessarily associate it with something from the late Cretaceous or even the Middle Cretaceous. So switching from our geological data sets, going to the geophysical, we used regional magnetic data as well as some localized, regional magnetic data as well as localized radiometric data. So this include database files as well as rasterized images. The database files needed to be stitched together using Geosoft Oasis Montage. And here we have examples that were given to us as residual mag and as well as the vertical derivative. Now, using Geosoft Oasis Montage, we were able to provide multiple magnetic maps. Here we have a workflow from the vertical integration to derive several different types of magnetic maps, including tilt derivative, analytical signal, and the horizontal derivative. Each one of these plays a different role in how we would understand the magnetics in that area. So one of the things we want to do with the geophysical data is link it with our metallogenic vents that we grouped in. So looking at the lithologies, we're able to create geophysical borders possibly, and maybe start concentrating the look in those areas. The other thing we can do is we can correlate it with regional structures. The darker circles are the areas of interest, but we also have the black lines that associate with regional faults from the data sets. And here we're seeing anomalies that correlate with the tilt derivative, the vertical derivative, as well as some potassium radiometrics. So then also we have the stream sediment geochemistry, kind of like the whole package deal as the Frank Arnott competition was looking for. So we used high resolution DEM and delineated and generated a watersheds map. So using that and using the regional stream sediment geochemistry, we generated 11 element interpolation maps. Arsenic here is one of our examples. Now this is extremely powerful as this can show relationships that we may not see either with the lithologies that we generated or maybe in different elements. The other thing that's great about this is that it helps us understand fluid transport and enrichments. So here we have the DEM on the bottom with high concentrations of copper. So this is likely the source of where this copper is, and we do see a porphyry prospect in the database set as well. So this is a good correlation. The other thing we could do with this is look at multiple elements, like I previously said. Arsenic, lead, and copper both show linear anomalies in multiple areas in the north, central, and the south. And then lastly, I kind of already said this, but we can also associate this with the age correlations that we generated. Here we would have, in the Middle Cretaceous, 2 linear trends, one in the central area and then in the northern area. So I kind of went through the process steps quite fast. I wasn't sure how much time I would have, but the main purpose of this project wasn't necessarily just to produce some maps and say, that's good, this is good for the Yukon area, but we wanted to promote simplified lithology and just looking at it from a basic understanding. Not necessarily to say that, oh, in the Yukon, this is great, but what about somewhere else? This could be implemented with another area with open source data similar to ours. So the next kind of slides are just a step-by-step approach if someone was also to go into this, either looking in our area or possibly somewhere else. So like I said before, you would start with your original bedrock data. Restructuring this data, as well as using a 4D analysis, you're able to reconstruct your regional area and get a better understanding. Also derive possible metallogenic events that could be occurring there or magmatic belts. Using previous literature or provided data like the deposits and prospects, you're able to group this into metallogenic ages. Now this is great because now we can visually see how lithologies are linked to the known porphyry occurrences in our area. And again, just to reiterate, we can associate this with different time frames. So here we would have multiple different time frames that we would group into and separate from other known porphyry projects. Now that we have these lithological trends, we want to correlate it and verify it using geochemistry. So arsenic maps, great pathfinder element for gold, and one of our best produced maps, also verified with our lithological trends. Here we would have some in the central and the south. One of the larger regional trends in the Middle Cretaceous. As well, a larger one in the south. So they correlate quite well with the lithologies. So now we have the geochemistry and the geology. What about the geophysics? So looking in the central area of our project, using local radiometric data and analytical signal, they both produce anomalies that show in favor that there could be porphyry potential in this area. And as well as we look into the south, the residual data may not necessarily show any anomalies such as the middle area of our project, but the tilt derivative might show greater detail of lower amplitude anomalies that may otherwise be dwarfed by larger set anomalies. So using all these techniques discussed here, multiple regional trends have been identified in our area, prospects 1 to 4. They all share similar features such as geochemical anomalies, higher known porphyry occurrences associated with lithologies, some structural environments that look favorable, as well as some positive radiometric anomalies. In a regional setting, this would be more favorable for further investigation for local targets. Some acknowledgements and contributions, the programs that we used and the data, as well as special thanks to Dr. Kevin Ansell, Bruce Ingleton, Dr. Jim Merriam, Dr. Samuel Butler, and Garnet Wood, and as well as the Yukon Geological Survey for the data, and then the Frank Arnott for providing this competition. Thank you.
We've got time for a couple of questions.
Right.
I've got one. Oh, go ahead.
I just wanted to know, with your lake reconstructions, have you constrained your paleogeography? Like, how do you know that you're doing that?
Sorry, could you say that again?
How have you constrained your paleogeography in the lake reconstruction?
So using various data from PaleoGIS or the G-Plate software system, they have a large database set on various volcanic, plutonic, metamorphic, and cooling ages, and those constraints are what we use.
My question was calibration sites. There are, I believe, a few porphyries in that terrain, but I'm not sure if I saw them identified. Can you comment about whether you found them or they were just, yeah.
Like known porphyry deposits?
One comes to mind is Casino.
Yes. So Casino was in the fourth map, Casino nucleus revenue. Yeah. The trends that we did identify did have known deposit occurrences, but it's not necessarily because that we followed the data points, but the lithologies associated with it was the stronger case. Yes.
Okay, well, thank you very much, Ty,
Thanks, Ty.
and your colleagues.